So I'm throwing myself into the future, which we'll talk about now, which is nano architecture and molecular engineering. Richard Feynman in 1945 predicted that he will be able to select molecules and atoms and put them together one by one and one of certain chemical content and produce any substance we want. One will be a new metal, 50 times the strength of steel. Imagine what you do if you're designing with that. How slender and how strong these will be. Buildings will not ever be the same again.
This is a program on nanotechnology, nanotechnology in architecture. The previous clip you've just seen is of John Johansson, a famous figure in the world of architecture and nanotechnology, who sadly died in October 2012, just as we were going to film him. John Johansson studied under Walter Gropius and was part of the Harvard Five alongside Marcel Breuer and Philip Johnson. In 2002, he published A New Species of Architecture, a book filled with futuristic projects based on advances in biology and physics. He described it as an exhortation to the younger generations. Nanotechnology, that's 1/1000th of a meterology, is the engineering of functional systems at the molecular scale. Prince Charles, you may remember, caused something of a fuss when he reportedly warned of grey goo, nanotech robots devouring everything as they self-replicated. In fact, he denies ever using the phrase, and it was the man who coined the word nanotechnology, Eric Drexler, who raised the issue in his book, The Engines of Creation. These are so-called quadrotors or quadrocopters, model mini helicopters. Flight assembled architecture was conceived and built by teams at ETH Zurich. This is a scalable project where the quadrocopters are programmed to interact, lift, transport and assemble a building from a 3D model with no human intervention. No one is steering these robots except themselves, remotely responding to the changing circumstances that they find before them. Nobel Prize winner Richard Feynman's dream of a billion tiny factories maneuvering things atom by atom is on the way to becoming a reality.
In this project, we use teams of quadrotors to autonomously build cubic structures for modular parts. We developed a gripper to enable the quadrotor to pick up parts either vertically or horizontally. Magnets embedded in the parts allow them to snap into place when close to the desired position. By applying a yawing moment, the quadrotor can determine if parts have been placed successfully, and if necessary, retries until a solid connection is made. Using multiple quadrotors allows structures to be built more quickly. Our algorithm can construct nearly any tower-like structure like the ones shown here. We are only limited by the battery life of the quadrotors and the number of parts available.
Exciting stuff, even though it's a little bit creepy. Okay, so in this program, we now talk to two leading science communicators. discussing things of an even smaller nature. Rachel Armstrong is a world-renowned writer on biotechnology. She will be discussing practical and moral challenges for what she calls living architecture, advocating using advanced new technologies such as synthetic biology to advance architecture of the future. But first, Viv Regan caught up with Chandra Harkness, director at the Cheltenham Science Festival, to take a look at some of the emerging possibilities for nanotechnology in construction.
So, Chandra, can you start by telling us nanotechnology's hyperreality? I mean, what's relevant about it? What's interesting?
Nanotechnology covers a lot of different things. You're basically talking about anything that happens at the very, very, very small scale, the kind of scale where you can't even see it with a conventional microscope. You're talking about the atomic scale, really. What's exciting about it is when you get down to that scale of detail, you can actually change the way materials behave. So, for example, in nature, carbon is the same stuff, whether it's in graphite or in a diamond. It's exactly the same element, but the atoms fit together differently. So with graphite, the atoms fit together in layers, but the layers slide over each other, which is why your graphite pencil can slide across a sheet of paper, leaving a layer of graphite that you can see. A diamond is exactly the same stuff, but it's bound together really tightly. So it's one of the hardest substances. You can cut anything with it. And yet it's made of the same stuff as graphite. So with nanotechnology, what you essentially do is you can change the way materials behave by manipulating them at that atomic level. Or you can get materials that behave a certain way and use them at that practically atomic level to get different effects that you want without necessarily even being able to see or perceive them with the naked eye. So it covers lots of things. I mean, you can buy face creams with nanoribolipsomes in and go, oh, that's really sciencey. But, you know, or you can have industrial coatings for things. It covers lots of things, but they're all essentially happening at that very, very small scale.
Great. And what graphene is said to be the new wonder material. What is it?
Well, graphene is a very good example of this. Graphene is also carbon. And in fact, graphene is something you can kind of make at home. If you get a soft graphite pencil and you scribble all over a piece of paper and you then take some sellotape and put that over and press it down, and you will get a layer of pencil graphite on the sellotape. And that is essentially what graphene is. It's a very, very thin layer of graphite, like an atom thick in some places. So it's almost not there at all. But it has lots of interesting properties because it's so very thin. It does things like you can conduct electricity with it. It behaves in ways that you wouldn't necessarily expect carbon to behave when it's in a different form. So they're really just at the beginning of exploring all the things you can do with it. But it is a great example of a brand new material that has all sorts of possibilities that we're just at the beginning of finding out.
And what about nanotechnology's effect on the properties of everyday construction material? I mean, I'm thinking concrete. What are the possibilities?
There's two different ways nanotechnology can help. One is simply looking at the way the concrete fits together, again on the very, very small scale. So obviously concrete is made up of different materials, and what gives it its strength is that as it sets, crystals form inside the concrete and the crystals lock together, and that's what gives it its solidity. And you can actually manipulate by looking at the materials you put in and the way the concrete is made and set. You can manipulate how those crystals form, how they fit together, and just change the properties of the concrete without altering the ingredients, if you like. You think of it like making bread in two different ways. You get a different structure of bread, even if the ingredients are the same. But the other thing you can do is you can add different things to the concrete, because I mean, concrete on its own is very strong that way. It's very good weight bearing, but it's quite brittle. You think of a bar of chocolate, for example. You could put a lot of weight on a bar of chocolate, and unless it melts, it's not going to squash. But if you snap it like that, it's got no strength at all. So concrete has this kind of, it's very it hasn't got what you call stiffness, so it can't resist being bent very well. It just snaps, but it can take a lot of weight. And the traditional way to deal with this is to put steel reinforcements in, because steel it is very good at, it's got a lot of stiffness, very good at resisting movement that way. But then now there's new ways to do this, so you can add in different ingredients that give that kind of resistance to snapping inside concrete, just by adding nanoparticles of other materials, or even fibres of steel, very, very tiny pieces of steel, to give that steel-like property to concrete. It's called ultra-high performance concrete. And it's so stiff that you can just use blocks of it to make entire bridges. You don't have to put the steel reinforcement in, and they're already starting to use this. But again, as we build, I mean, you can see in the city we're building taller and taller, so that property of concrete to hold its own weight without reinforcements is going to be more and more useful.
Yeah, and is there any other interesting stuff happening?
Well, yes. I mean, there's actually, looking at concrete and the way concrete tends to weather and wear, we're now looking at ways, not me obviously, people are now looking at ways to repair concrete. So if it gets cracks, for example, you can use polymer-based repair materials that will make the concrete stronger, because they can go in and actually go in the gaps in the solid material. And give it more resistance than it had before, actually give it more strength than it had before. And in fact, not necessarily in concrete yet, but in other materials, scientists are looking at self-healing materials. For example, they're looking at this for things like aircraft wings. So a material that knows when it's got cracks forming and can actually close the cracks up and heal itself. So that you won't get the same problems of material fatigue, the things just gradually wearing out, that the material will go, oh, I've got a bit of a crack forming here, I'm going to melt and reform and repair myself the same way that your skin repairs itself. So obviously that's got massive potential for safety and for reducing maintenance costs.
Yeah, and I've heard that there's self-cleaning glass, which I'm particularly interested in. Tell us about that.
Yes, well, yeah, and it's very interesting. We're here in the, again, it's a very, very tall building, and you can see on the outside of the glass that there's dirty marks where, just from raindrops, really, just from the city rain, and obviously dirt washing down off the building. And at the moment, what has to happen is somebody has to abseil down the outside of the building, or come down in a kind of gondola thing and clean the windows from the outside. So one thing that's really exciting that is already in use is tiny nanoparticles of titanium dioxide, and you coat the glass with that. And again, it's too thin. It doesn't block the light coming in because they're so tiny. But what they do is dirt will then attach to those. But when sunlight hits them, then the reaction with the titanium dioxide particles starts to break down the dirt. And then the next time it rains, the rain washes them away. So you've effectively got self-cleaning windows. And those titanium dioxide particles are the same thing that they put in sunscreen, because they reflect the light away. Obviously, they're doing a different job there, but it's the same stuff.
Marvellous. And what about the future?
In the future, it's got enormous potential. I mean, there's materials that you can improve the performance of existing materials. There's new materials. I mean, you talked about graphene. There's new insulation materials being developed. There's a wonderful material called aerogel, which NASA sends. This is how cool this stuff is. It's the least dense material. It weighs so little you cannot feel the weight of it. It's almost transparent because it's mostly made of air. It's over 95% air, but there's just enough material there to hold it together. NASA use it to catch particles in space and then bring it back to Earth with these particles of asteroids and comets and so on embedded in them, so they can study it. But because it's got the very tiny bubbles of air trapped in it, it's a great insulator. So all sorts of new insulation materials are on the way, which will make it much easier to keep houses and offices warm and quiet. But the carbon, again, I don't know why carbon is such a great material to work with. Maybe it's because it's easy to bond in different ways, but you can make artificial structures in carbon. You can make things called buckyballs, which are named after Buckminster Fuller, because, well, the real name is Buckminster Fullerene. He was the guy that designed geodesic domes, which use a kind of geometric structure to make something that's very strong. And it turns out you can bond carbon atoms together in a very similar way. So it looks kind of like, if you could see it, it would look like a giant football, those kind of polygons all over it. And they're enormously strong. And you can also, using a similar design, you can bond carbon together into a tube, which again, it makes it immensely strong. If you think of a piece of paper, if you have a flat piece of paper and you try and put weight on it, it's got no strength at all. But if you roll the piece of paper up into a tube, then it's much stronger. It's stronger that way, and of course it's very strong that way. So you're doing a similar thing with carbon. You make it into nanotubes, and you've got this enormous strength, but it's very light because again it's mostly air. And you can make fibres out of those. They're even talking about building a space elevator where you get a cable from the Earth to a geostationary satellite, and you use that as a lift. So you use it as a lift cable and move lift compartments up and down it, and that's how you get into space instead of rockets. And for years they've said, well, it's a great idea, but how could you possibly have a cable that long? It would be too heavy. And they're now starting to say, if you used carbon nanotubes, we reckon we could get a cable that was strong enough and light enough to go all the way from here to a satellite and have a space elevator. So that's pretty exciting.
That is really exciting. Oh, brilliant. Oh, Timandra, thanks so much for opening up some possibilities for us. Thank you. Back to Austin.
Thanks, Viv. Well, before we go on, let's have a brief interlude with the potter's wheel. Pottery for the Modern Age. That was a series of clay mixed bricks made by a rapid prototyping 3D printer in Holland. But finally, I caught up with Rachel Armstrong at the Building Centre in London to ask her about some of her views on bioengineering and nanotechnology.
Essentially, bioengineering is a kind of synthetic biology, the design and engineering of living things. And I think bioengineering for me suggests that there's still a lot of bio present, and it's essentially a top-down kind of intervention. So I think bioengineering exists on the scale where the software is present, whereas nanotechnology per se is really the tiny formal bits of structure. I'm very keen to get away from the idea of technology as a gadget and a method of revealing, which isn't necessarily located within a machine. However, that doesn't mean that humans have absolutely no agency. Technology, for me, are the instruments and interventions that humans make in order to represent themselves in this world. So I think that the Cartesian idea of the body is a very simplistic one. And I think that if we actually rethink about what it means to be human and put an ecological framework at the heart of that, I think we start to imagine our interventions and their consequences in a very different way.
In terms of the interactive facades, the bio blocks, bio bricks that you use, as well as the discussion about Venice, which you're very well kind of known for. Can you just explain what the proposition is, what the problem is, and what your solutions are?
So the problem that my work tries to address in architectural terms is the status that materials have when we're making a building. And currently that status is that materials are passive, they require human agency to be produced and then constructed into forms for living in. And the issue with that is that essentially as soon as a building is made, it starts to exhibit something called redundancy, because it's been imagined as a simple system or an object within a much more complex network of, I guess, natural forces, which may come from, you know, the use of the building inside by humans, to the way that, you know, lichens and mosses and birds, you know, may use the exterior of the house, and also the contribution that the passive, you know, the use of passive materials in those kinds of environments make to our surroundings, and therefore the quality of our living spaces. So the question becomes, okay, well, if we elevate the status of materials and actually focus on how these may actually contribute to a quality of life and a quality of our living spaces, then what does that actually mean? So I've been working with materials that possess some of the properties that you'd attribute to living systems, so movement, sensitivity, the ability to produce materials spontaneously when they reach certain conditions, and seeing what those kinds of propositions might be.
This is some footage provided by Rachel Armstrong looking at oil water droplets, which Rachel Armstrong suggests might be exhibiting some kind of social behaviour. Her views are a little challenging.
So, for example, the idea of a living facade, maybe housing an algal and a bacterial population. Maybe the algae use sunlight and carbon dioxide to make organic matter and biofuels, which are good for the algae. That's what they grow on. But it could also be used by people in an urban setting, almost like a kind of window farming. And you know, they could make paper and use oil that may be used to heat or drive machines, or part of the building technologies that are already existing. So that's kind of one aspect. And I mean, the other aspect of thinking about materials in a different way is to not necessarily imagine everything being living, as it were, but literally finding sites of abundance within an urban landscape in which maybe the access to wind or solar energy or even chemical energy or thermal energy from the ground becomes very site-specific even within a building. So I guess in some ways it breaks the idea of the landscape in a building down into little niches that we can think of as being appropriate for different kinds of materiality. So we study that landscape and think about what kinds of material systems would work well there, and what their relative impact will be on that part of the building. And I guess to imagine the building itself as a kind of ecology in which there is resource abundance and resource constraints, and that each one is unique. So I mean, in some ways it's really tied into skins and facades, but I guess there's a slightly more building as ecology aspect. So the question whether or not a quick technological fix, say for example putting a load of concrete underneath the city of Venice to stop it drowning, would be better and less problematic than, say, growing an artificial limestone reef underneath it, is an interesting one. But I think that the approach to that is that they give qualitatively different kinds of results. And so then it becomes an assessment, again, a community, maybe a world assessment as to which of these interventions is preferable. I mean, so essentially the protocell limestone reef does have this capacity to reappropriate whether it is sinking or drowning. It is a longer term intervention, and as such its materiality is different. That doesn't mean it's better or worse, it just gives a different quality of architecture, whereas the concrete geometric foundations gives a different kind of product, which may or may not be considered acceptable.
My final question, which arises from that, is your idea about collaborative working, how this was more than just a technical issue. Yeah. It's a way of actually trying to understand how we work. So you just explain what the collaborative model is that you're looking towards. Yeah.
So part of my research is not just about developing a model of materials and a technology that helps us intervene or reveal differently or different truths about our world, but actually a way of working, a practical method for collaboration between partnerships that really, you know, don't come from the same ontological understanding at all. And in this way, I've been working in what Isabel Stengers would call an ecology of practices. And this is a constructivist approach to collaboration that enables us to sit together without hierarchies of knowledge, without a premise that we actually know the answer of something that we're trying to connect with, and instead allows researchers and industrialists and politicians to what she describes as dreaming along with each other. And I really like this idea as a collaborative method, because the constructivist aspects is that the transformation is not just in terms of the outcome or the solution or the further sets of discussions that you might have, but the actual internal changes that each of the participants experiences when they're working with people that have very different knowledge sets. And so it's actually a time of reflection as well as, you know, the delivery of your expertise or your views. And so that collaborative constructivist approach I've actually not just developed in my materials experiments, but actually also in the partnerships that I've been building.
On that point, fantastic. Okay, that's it. I hope you enjoyed it. I'm sure we'll be back with more emerging technologies in the future. Until then, goodbye.